Everything we've done so far has been limited to a single qubit. One qubit means one copy of our Hilbert space, C2, or as we call it, H. We'll need multiple qubit processors and algorithms to do anything useful, and this week we check off a box called Tensor Algebra that powers the step up from a single qubit to 2 qubits. Today we'll learn second-order tensors. They'll upgrade us from 1 qubit to 2. But the math also works to get us to 3, 4, or any number of qubits, so there's no reason to complicate the notation. We'll learn second-order tensors today, and in a very brief lesson, just a couple of pages next week, I'll walk you through how all this works with no change for higher-order products. A second-order tensor product is constructed from 2 component vector spaces, say R2 and R3. Notice that the spaces can be different dimensions. From there, we have to define the new product space. Students sometimes have a hard time with tensors because it's natural to believe that the vectors in the product space are themselves tensor products of 2 vectors, one from each component space. But that's not true. Yes, we do start out by including those so-called separable tensors in our new, bigger space, but from there we have to build new vectors that are sums of those separable tensors. And those sums may not be decomposable as a simple product of 2 component tensors. Thankfully, once we form all possible finite sums of separable tensors, we have the full product space, and all we need to do then is describe how to add the new, larger vectors and do scalar multiplication. Each concept in the 2 component spaces is used to induce the corresponding concept in the product space. For example, the 2 individual inner products give rise to an inner product in the new, larger space. And the 2 component bases can be combined to generate a basis for the product space. The details dictate that the dimension of the product space is the product of the dimensions of the 2 component spaces. So, in the case of R2 times R3, the tensor product space will have dimension 2 times 3, or 6. If V has dimension n and W has dimension m, then the basis for the product space consists of the n times m separable products formed from the 2 component bases. And all other vectors in the product space are linear combinations or superpositions of those n times m special separable tensors. When it comes to computing, I'll show you some easy rules, which admittedly take up a lot of page real estate, that can empower you to construct tensor products by hand and sometimes in your head. There are always 2 ways to look at the basis for the product space. We can view it as all possible separable tensor products of the component bases, or we can consider each new basis vector as an entity in itself and just look at it as a very large column vector that has a 1 in a particular position and zeros everywhere else. The next big topic is linear transformations, or operators of the product space. It works very much like vectors. We first form separable transformations, which are induced by individual operators on each component space. But there are many transformations in the product space that are not separable. Those can only be formed by adding separable operators. The separable operators are easy to recognize and even compute because they have a special form. But we'll be using non-separable operators too. In fact, some of the simplest and most useful product operators turn out to be non-separable. You'll learn all the tensor product concepts and moves today, and we'll put them to work with real 2-qubit examples in the next lecture. The secret to working with tensors is to remain calm and always know where the definitions are so you can go back and read and reread them when you get stuck. And for us, all the definitions are right here in this short chapter.